Okay, I am officially out of the Excel tournament for this year. I came in the top 32 and then was eliminated by Peter Schall, which is kind of what I expected, and I was just kind of thrilled to get this far, given that it's only my first year competing. I've made good progress. If I can continue on that trajectory, I should do even better next year. Anyway, with that said, I thought I would share a crazy, powerful Lambda that solves many questions in many map cases that you guys can steal if you want to. It's very long, but it's super useful, and I'm going to show you how quickly it can blast through any map cases. So, the Lambda is here, and I will try to briefly explain what it does, and I will break this down. So, it's essentially taking three mandatory arguments: a cell address, a map, and an extension value, which is basically how far you want to travel from your given cell. So let's add those onto the end. So let's take this highlighted cell here, which is L4. L4, our map, we can just highlight here. And then our extension, let's just say something like 20 so that we capture that whole map. And what this is going to do is going to spit out that map in a column format with everything that's on the map, an address for that thing, and also a distance of how far it is away. And this by default allows diagonal distances. So L4 is 0 cells away, it's the cell we're on. And then around this L4, we have three O's here. This is kind of laid out like the portal case if you did that recently. And you'll see those here in L3, M4, and K5. Now, within this Lambda, there are two other Lambdas used. The first is address of cells, which gives me the second column. So that is this Lambda here, if you want to copy that. And what that is doing is it's basically giving me address of any area that I highlight. So within this Lambda, we are taking that is this line, and we are just two-calling the address. The visual is basically pulling out an index of our map based on our extension value, and it's taking into account the bounds of the map. So all it's saying is my extension is 20, so I want to take this, the row and column of this cell, take the minimum of the row or column of the map and our extension, and give me that index back. And this Lambda works very quickly because I'm actually taking a small section of a map and then the rest of the Lambda works off that. So even though it has indirects in, if you have a giant map, as you'll see in a minute, it's still extremely fast. So the first bit is just my visual, that's basically taking out part of the map. My second part is the address, which is the second column, and then I have a bunch of row distances and column distances calculated here. So row distance, column distance, which is, you know, exactly as it says, it's calculating in the same columnar format the distance from my chosen cell and every cell on this map. So the next thing I'm calculating is a distance, and it's using this distance Lambda, which is here. So this is essentially, I can take two cells, so E4, E5, for example, and then if I say distance, I can click these cells and it's going to give me the distance between them. So the distance between those is 1. If I put E57, we have a distance of 53. You know, F would up that distance by 1. Actually, it wouldn't because it's diagonals. And what I can also do is I can have an optional argument for whether diagonals are allowed. So I can say 1 means restrict diagonals, so that distance now becomes 54 instead of 53. If I went to E, F, G, H, you know, that's going to add steps to get across. I can also choose 2, which is the straight line Pythagorean distance between two cells. So that is essentially, if I split this Lambda out, give me 1 second. So what this distance Lambda is doing, it's taking the row distance between two cells, the column distance between them, the diagonal distance between them, which is just the by row max of the row and column distance. It's taking the total distance, which is adding the row and column distance together, and the straight line distance is both the distances squared and then the square root of those. So it's just the Pythagorean formula basically. And then my output is saying, if we have 1 as the optional argument, give me the total distance, which is the restricted diagonal. If it's 2, give me the straight line distance, otherwise give me the diagonal distance. Now, the reason I've recalculated row and column distances here is because sometimes there's preferences where you would like to go. So in this example here, we have 3 O's around the X. We would have to choose which one of those O's takes priority. So the total distance here is just basically my distance formula, and I've had to amend it to say whether arguments are included or not. I have then sorted the table by the total distance and this sort argument, which I'll explain in a minute. And then I am omitting blanks, so if some of this map had blanks on, like that, it's only going to show me the things that are there. So if I got rid of, you know, all of that, there are minimal things left on the map. And now let's explain the next argument. So the next argument is where I can restrict diagonals. So 1, I restrict diagonals. So you'll see now we only have 4 things that are 1 cell away, and the corners are actually 2 cells away. I can also choose 2 for a Pythagorean distance. And then my next argument, I'm just going to remove that so it's back to diagonals. My next argument is whether I'm looking for an exact item. So if I was looking just for the O's, I could put an O there, and it's only going to give me where these, specific things are. And the order is going to give me 8 possible orders. So I've tried to label them in this top bit here. And this is basically saying row, column, ascending, ascending, column, row, ascending, ascending, and so on. So basically, row, column, ascending would be, I prefer to go to a smaller row, and then if there are multiple things there, I would prefer to go to a smaller column. So in this case, if I put the optional argument with a 1, then we should see that the first preferred portal is K3, which it is. Then it's going to be L3, and then it's going to be M4, K5. If I put the order as 2, it's going to prefer a lower column first, then a lower row. So the first cell should be K5. Oh, sorry, yes, I haven't highlighted this. So the first preferred row is a lower column, which is K, and then I can change this to change whether I prefer to go lower row, column, or higher row or column, and then again off of that, lower or higher. So there's basically 8 combinations. And I'll show you in these examples why that argument is important. But essentially this looks quite complicated, but if you copy it in, the usage is actually quite simple. So let's get into some cases. So the first case, I've shown this example before, is this spreadsheet is a nightmare. You have a big patch of aliens and ghosts, and the final question, you want to find which one is closest to you. So for this, I can just say closest on map. That is my cell. Here is my map. And my extension, we could try, I don't know, 6, for example. And that's just going to give me all of the things on the map in order of what's closest. So I can just index this first row, second column to get my answer. So index 1, 2, and I have my answer. I can then just drag that down. And as you can see, it solves this really fast. And one of the bonuses on this was to figure out how many aliens were in this question. So I could just take 1, 1 at the end instead, and that gives me what's in the cell. So that's a real quick example on that case. The next example I will show is this numbers game. You essentially had a grid of things that are in either numbers or hexadecimal format, I think, where you can go A for 10, B for 11, and so on. And one of the questions is asking you to pull out a 9-cell square around an address. So again, I can say closest on map. This is the cell. This isn't really a map case, but you'll see the usage. Here's my map, and I want an extension of 1. So there we get the 9 cells that are around it. We want the first column, so we can say take first column. Then in this question, we want to convert it from hex to decimal. So hex to decimal of all of that stuff is going to give me, the answers, and then I can sum it up. 69, and those would be our answers on this question. Now let's get a little more complicated, where we add a couple more arguments. So on this case, we had a map like this, road to Las Vegas. We had cactuses and stuff like that. One of the questions is asking how many of these items are 10 cells away from you. So again, closest on map, we have this cell. Here is the map. And we want to go 10 cells away, so that's going to give us everything. And then we have an optional argument here to filter for an item, so it's this item, and it's going to only show me those items. So I can simply do rows of that, and that's going to be our answers for this one. Next up, we'll go with a recent case, portals. So you have lots of maps here. This is kind of the example I showed, and you want to walk to the nearest portal. However, the added complication here is that you will prefer, when there is multiple matches, to go down a column and then down a row. So that's where the argument of ordering is going to come into play. So let's pull out the map of the given area. So this is basically, these are the areas you're in, which is the tab number. So I'm just going to set this up. So I'm going to say area and this and that. So that's my map. There we go. So we can say closest on map. Our cell is this. Our map is what we've just put there. our extension, we can just put, actually, this one is also more complicated because you cannot move diagonally. So let's just put an extension of something fairly big, 30, so we capture everything. And then we have no diagonals allowed, so we put a 1 there. The item is a portal, so it's a 0. And then our order actually matters here. So our order is column and then row. So that's the second argument in this optional list here. So it's 2 is the sort order. And this is going to be where I prefer to go G4, and it's 5. So we basically want to index first row, third column. That's our distance to the next portal, which is what this question asks for. Then the next question is asking what cell do you go to, so i.e. what cell is the closest portal in. That is just the second column in my array. So that solves that. And the final question was just to do that over and over. So this is super easy. I can just copy this across and I know all the distances. I've refined this Lambda a lot, so now it's pretty streamlined. Now let's go for the census case. The final question is pull out an average weighted life expectancy of a given kind of area on a map. So here we have, a cell, so let's just text split that. And we want a +2 to it in this case because the map is 2 cells out from where we are. This setup doesn't really matter to show you the example, but that's going to be our starting cell. So let's just say address here, 4. Okay, so that's our starting address. So let's do closest on map. Here is our cell. Here is our map. And our extension is actually listed here. We can only go 6 radius away. And we're in Pythagorean distance terms. So that's the second optional argument here. The item doesn't matter and the order doesn't matter. So that's going to pull out all of our cities that are within that radius in Pythagorean terms. So we can just take the first column and then to finish this question, I won't do it now because it will waste time. You're just going to look those cities up in here, pull out the life expectancy and the population, and you can just do your calculation, in a data table and answer these real quick. Finally, an even more complicated example. So the number 1 fan Lana Banana question. We start from a cell and Lana Banana goes to the closest banana and she prefers to go to a lower row then column. So the ordering is basically like a 2-col. If there was ever a question where the ordering was more complex, this Lambda kind of solves it for me without having to mess around. So we can say closest on map, here's our cell, here's our map. Our extension, we can just go something big, let's go 40. Diagonals are allowed here. The item we're looking for is a banana. And our order is 1. So this is going to give me a list of bananas in preferred order that she takes from D4. So D4 is already on the list, so we want to eliminate that. So on this question, what we do is we would say D4 is where we go. I want to choose col 2 of this. And we have a list of all preferred bananas. So let's say, let A be that. And we're going to filter A where is error X match A in here. And I'll explain in a minute why I'm doing it this way. So that gets rid of D4. On this question, we want to get rid of bananas that we've already collected. So all we would have to do is know that we go to C2. So let's put that up here. So let's just pull that across in our formula. And then we can pull that across here. And we know that this is the order bananas would be collected. So you can see in the example here, we go D4, then to C2, then to D2. And then at that point, we would stop because the question is saying where the edge is closest, you move off the map instead of collecting the banana. So in this case, we would have collected 3 bananas, which are here. So all I would need to do now is just do a calculation to see whether the edge is closest or the next banana is closest, and I can pull out the next banana from that closest on map formula. So it's a very useful lambda, at least for me. It's quite complicated, but if you want to take it down, feel free to copy that, and yeah, it will save you a lot of time. Anyway, that's it. I hope this was useful.